Hello, everybody. My name is Sunil Pareek, and today in this session, we will continue our discussion on SRv6. This is our first session, or technically, I can call it second session, where in the last session, which we called as zero session, where we covered some of the basics for IPv6. We have started from the scratch on IPv6, and then we slowly transitioned towards SRv6 by visiting some of the key limitations in IPv4 and how over a period of time these networks have grown to become complex. And we will see that how SRv6 can simplify the networks. So with that, this is actually our first session from the SRv6 point of view, but technically it is second. If you haven't seen the session zero or the earlier session, I would highly recommend that you just go and see that. This session, I will be simplifying the SRv6 concept. So this is again for our beginner audience who or the people who have spent somewhere around 4 to 5 years primarily into the service provider domain where they have some basic understanding of MPLS networking. So with that, what we will be looking at today is, of course, we will touch base on our previous topic. We will revisit some of the IPv4 limitations, and then we will look at how SRv6 is addressing it. We will look at this SRv6 SID structure. Is it just a 128 bit of IPv6 address, or is there is anything more to it? Then we will understand the why behind Micro-SID, and we'll also look at what this Micro-SID is. And towards the end, we will look at SRv6 packet forwarding in some scenarios, including L3 VPN as well. So with that, what we discussed in our last session, if you recall, was this slide where I was highlighting that how over a period of time these things have added over IPv4, which had resulted into the complexity. After that session, some of you have reached out and asked about the few stories that I have talked into that. Was those real or it was just for the session? So I would like to say those are the real stories that I and my team had seen, but those stories had spanned across several years, 7 to 8 years, which I had just confined and told you in like 50 or 60 minutes of that session. But yes, those were the real incidents that had happened in the past. But after a certain time when I was working for this provider, we have implemented most of these things. I switched my gear and I moved on to the service providers to a product-based company where my job is to advise these SPs or enterprises on how can they simplify their network. But I still talk to my previous team, and after that, there is this Mr. Amit who had taken over from me. He's still there, and I often talk, and he was saying that whatever was there when I left, this complexity has gone in the upward direction. What he meant to say is that there are more number of TE tunnels now that they are provisioning based on the customer demands. There are a mix of layer 2, layer 3 VPNs, and on top of that, they had also started giving the multicast, which is in SP's term is called MVPN services, and introduced some other vendors routers as well. So now the network has become more complex than what I had when I was there, and there are so many operational issues that even it is causing some issues to the SLAs. So that's where this guy Amit, who is heading that team now, was asked to simplify the network. And as a first step, he was approached by some vendors, and then he had those discussions like how can this transport network simplify. And I was also having some calls with him on like as we know each other based on the relations, and he was showing something like this, where this was their current state, where they have IGP for reachability, LDP for label distribution, RSVP for T, and then on the overlay side, they are providing all these VPN v4 based services, and now VPN v6 is also there. So they are using this MPBGP. To that, what Amit, after consultation with all these vendors, were considering is that they should go to SR. And what they were considering is SR-MPLS, so that the data plane stays the same. They just move their control plane. And what is the advantage when they move from here, like position number 1 to 2? They can get rid of this LDP, they can get rid of this RSVP, and they can get rid of this BGP LU also, considering the scenarios how it was deployed there. And it's a simple IGP network where IGP is responsible for distributing the labels. So you don't need a separate protocol, and the data plane is not changing. But then in the meantime, he was also doing some research, and he thought that, okay, when we are making this transition, is it the right step? He was asking to me that, Sunil, is it right step to move to SR based MPLS, or can we further simplify and go to SRv6? And that, well, when he was talking to me, I remember when I was working there, we uh, took part in this IPv6 day, which was celebrated somewhere around 2012. I don't recall the date on top of my head, but what happened as a part of that is we had also started looking at enabling IPv6. Though it was very scattered in some part of the network, we didn't had a, I would say, a perfect approach to enable IPv6, but we did some assessment, we started enabling it. So that's where he was asking, like, either we should we go here, or we should further simplify and go to SRv6, where IPv6 is the data plane, and then you have this IGP, and for the overlay, it is MPBGP as they are running today. So his thought was right, but can SRv6 further simplify the network? Yes, it can. And then this discussion went into some other direction, but he, as a part of this, he also wanted to understand this SRv6 as a technology. It's new and very limited vendors are using it, but though the benefits are amazing. If you look at from the support ecosystem for SRv6, it is even supported on the Linux side. It's supported by multiple vendors, including Cisco, Juniper, all the leading vendors on their platform. It's even supported by the Intel NICs as well, right? So, and then this support is there for quite some time. And by the way, there are some operators who are running SRv6 currently. And I do foresee that considering the simplicity that it offers and going through all the pain that the operator had taken here, it will be much more simplified here. So our discussion went into two directions. So what is one question is whether they should consider SRv6 versus SR-MPLS. Let me park that. We will cover it sometime later. But his other query was like how exactly this SRv6 work? What are those fundamentals for SRv6? And I told him that that is more important for you right now to understand, and then you can have these discussions with the vendors, whoever you are talking to. So that's where we started some discussions around this SRv6. So SRv6 SID, which is basically a segment identifier, it's as we had seen in our last discussion also that there carry some set of network instructions where your packet itself contain that information where exactly it needs to go or what all network functions it has to pass through before it reaches to the endpoint. If this is something that doesn't make sense, let's revisit this with a diagram, and after that you will be able to understand what I mean by the network instructions and how a SRv6 segment routing header carries this. So this was the slide I took from our last session where we ended our first session, where our requirement was that there is this source and it's originating a packet, and due to some requirements I want it to pass through R1 to R2 because this can be, let's say, a low latency path, and I am selling this SLA based service, so I am routing this customer via this path. And then or this R2 can be some security VNF or firewall, let's say, where I want this traffic to pass through the firewall and then come back to my network, and R3 is the endpoint. So how can we do this with SRv6? So at the source itself, what we do is we in the segment routing header, we encode all these instructions, IP address 1, IPv6 address 2, and 3, which are like this is your R1, this is your R2, and this is your R3. And then this bottom address or this last address is copied here, and the packet is simply IPv6 routed. So between S and R1, there can be many hops here. What they will see is this, and they will simply route the packet towards R1. Once the packet reaches R1, R1 will see itself that this address is local to me. So it will go ahead and examine this SRH. Are there any next hops into that? Then it will say that yes, Now it need to go to destination address 2. So I will simply replace my destination address with IPv6 address 2, which is by the way of R2, and packet will go there. And same operation will happen here where I will copy this. And finally, after that, there are no addresses left. So this is my endpoint, the end destination. And it is all simple plain IPv6 routing that you see here. Right? No labels, no other control plane, only IPv6 routing, IPv6 IGP. Now, the question is, we in the last slide, I was using one term called SID, which is segment identifier. So is this SID is simply this IPv6 address, or there is anything more to it? Can I call this, like I had shown you this simplified diagram. Now we will put more meat into the discussion. So this IPv6 address that you see here, now we will open it up and we'll see how exactly my SID looks like. So for the SID structure, let me take a backstage and explain you that there is this PE1. Here I have this PE2, and it's connected like there is PE3, PE4, like this. It's a simple topology, and here I have my CE1, here I have my CE2. I have provisioned, let's go back in the history and provision MPLS VPN layer 3. So if you understand MPLS, you will know that, okay, this will be in VRF. So I am naming it as VRF1. And here, between this domain, it will be LDP plus MPBGP. And what is the purpose of this is LDP is to forward the packet based on the labels. So there will be one loopback here, 1.1.1.1. Here it is 2.2.2.2. Again, I'm oversimplifying this, and I assume that you understand MPLS VPN a bit. So what will happen is for 2.2.2.2, LDP will allocate one label. Let's say that label is 50. So when a packet comes from here, this CE1, let's say this is 10.10.10.10, this is 11.11.11.11. So packet coming from 10.10.10 to 11.11.11 will reach on PE1. PE1 will see that, okay, this packet is reachable via 2.2.2. Who will tell that? MPBGP. So once the packet, once it knows that, okay, it is reaches via 2.2.2.2, it will see that, okay, what is the label for that? So the label is 50. LDP will tell that, okay, if you want to reach 222, you use the label 50. So it will use 50. P3 might have assigned some label. So actually LDP, it is hop by hop. So it will come here, let's say 40. Here it is 50. So 50 will come this side. So this is hop by hop. But it's just to simplify this discussion. The main point I will cover, or like why I'm talking about this. So this LDP is hop by hop. So P3, P2 assign a label, let's say 40, or if it is, if in technical terms, if you go, again, this is hypothetical, it will be implicit null label, which is the PHP. But this is not a MPLS class, so I'm not going into the depth of that. Let's say this is 40, and then here it is 50. So P, what it will do is it will encapsulate that packet, send it with label 50. 50 will come here. It will say that, okay, 50 need to swipe with 40 or implicit null, and then it will come here. Simple. Now, how this PE2 will come to know that it need to forward to VRF1? I mean, there can be another VRF here, which is VRF2, or VRF3 can be here, right? So how does it know? It knows via this MPBGP, where MPBGP will allocate the label for the prefixes, or it can be per VRF, where it says that for this VRF, the label is 100. And this label will be directly supplied from PE2 to PE1. So what PE1 will do is, it will put a stack of labels. So underlying innermost label will be 100 and then 50. So 50 will be used to reach to 222. And then when it reaches 222, what to do? That this underlying label will tell that, okay, 100 is allocated for VRF1. So you send here. So this is the important point that I wanted to cover. You see here, there are two labels, 50 and 100. 50 is, I want to reach to 222. Once I reach to 222, what I need to do is, that will be told by label 100. That is your VPN v4 label, right? Now, let's see how does this work in SRv6. So let me just clear this ink for a minute, if you can allow me. Right. So now let's see that we have this 128 bit of IP addresses. How can we encode that functionality of the LDP label, which is your transport label, and then the VPN label, which is your VPN v4 label, right, into this address? So for that, we split this. So there is this locator part, which tells that, okay, where to go, and then some bits are these function part, which tells like what is the action that you need to perform. When I say action, is it you need to forward this packet to VRF1, VRF2, VRF3, right? So that is encoded, and this is all encoded into this 128-bit address. So we are splitting that IPv6 address to perform the duty of transport label and VPN v4 label. And by the way, this function, right, this is only used, as you see, right, VPN v4 label, the intermediate node, the P3 or P4, they will not even understand that. That VPN v4 label will be understood by PE2 only, because PE2 is the one who had generated it via BGP. Same way, this function is only useful for the endpoint. Once the packet reaches to that end PE, then it will look at that function and it will execute whatever the instructions are or whatever the action is. So locator identify the endpoint and function identify the actions. I hope this is clear, but let's just look at it with one more perspective, like where exactly this SID comes from. So for the SRv6 to work, first of all, IPv6 has to be enabled. That is there. You did it because it is all IPv6 forwarding. So IPv6 should be enabled for this. So we have enabled this address, like we have allocated this address, let's say to node 1, right? Now I want to allocate a SID block to this. So what I will do is I will allocate a SID, and again this is a block B1 / 48. So I will allocate this block as a SID block. Why this is a block? Please hold that thought for some time. In this session, we will clear that. So this is my SID. But what you see here, this is IPv6 address for the classic address. And this is a SID block. Both of them can be different. So this gives you the flexibility that, okay, whatever IPv6 you are running in your network, when you are planning for SRv6, you can plan these locators with some other addresses as well. So this B1 here is the locator. So on node 1, this will advertise via IGP that B1 / 48 belongs to me. Then after B1 let's say B1 1 1 something. So this 1 1 can be a function where I can allocate this to any of the function that that node need to perform. If this is something that is not clear, we will again see this in the upcoming slide with some simulations. But the point here is that your SRv6 128-bit address is divided into two parts. Locator, it is the most significant bits used to route to the segment. Remember, transport label. Function is the least significant bit, identify the action, your VPN v4 label. So that's how you can correlate. Quickly, if I just show you the configuration of this, right? This is how SRv6 is configured. We will have, I will try to have some lab where I will show you, but not in this session, in some other session, because this is a series as we committed, right? So this is, there will be some more sessions for SRv6, but I just wanted to show you this, that this is how you allocate a SID block for a node. So FC001001 and then 2001/48. So this is how I allocate a SID block, and I have to enable it as you see here, right? My IPv6 address is not by default the SID. We will need to enable it, and this is the config. But just wanted to show you how this block is allocated. For the config, I would request please hold or give me some time. We'll look at the end-to-end SRv6 configuration. So now you understand that this 128 bits is divided into locator and function. Now let's move on to our next topic and talk about SRv6 compression. Why compression is needed? So let's talk about this scenario where on R1, due to these business reasons, I want you to take the shortest route to R2. Then you take the shortest route to R3. And from there, you take the shortest route to R4. And from R4, I want you to take interface 1. There are two interfaces here, interface 1, interface 2. And at 5, you decapsulate the packet and do a table lookup in the VRF. Which VRF? We will see. So you see here, right, there are certain instructions. Those are listed here. Let me park some of these instructions here. Let's say, let's park this one for now and this VRF for now. So what it means is that from R1, R2, R3, R4, and then the packet should go to R5, right? And I will tell you why I have removed those. So how does my segment routing header will look like? It will look like this, where from R1 will go to 2, then 3, 4, and 5. You see here, right? And as I was showing earlier, this address will be your destination address. Once it reaches R1, I will change the destination address to 2, then 3, then 4, then 5. Right. Now let's understand this with a very simple analogy where, let's say, I give a task to a courier boy where he need to deliver 3 or 4 packages, let's say. So I tell him that sitting, let's say, in Bangalore, India, and I tell him that you go to New Delhi, you go to Connaught Place, and then you go to shop number 100, deliver your first package. Then for the second package, you go to Delhi, you go to Connaught Place, and then you deliver the package to shop number 101. For the third package, you go to Connaught Delhi, you go to Connaught Place. By the way, Connaught Place is the location in Delhi, and then you deliver the package to shop number 105. So after some time, that courier boy will think that what I'm telling, I can simply tell him that, okay, you go to Delhi, you go to Connaught Place, and then these are the 4 packages that you need to deliver on 101, 102, and 105. If you see here, what exactly is happening here, this information is same for all these uh, segments, right? So if I can compress somehow, I can say that, okay, this part of my network is FCBB colon DB8 colon 0, let's say. So this part, this is the address that I had used for this part of the region, and then I am allocating, let's say, R1 is using 1, R2 is using 2, R3 is using 3, likewise, right? But first, wherever you are in the network, you need to come to this area, right? So I can simply say that to that courier boy, first you go here, FCBB DB8, and then you look for 1, 2, 3, 4, 5, right? So with that, can I save some space? Now, this was like a simple explanation, but if I come back to this, each of these IPv6 addresses that you see here are of 128 bit, right? And if, let's say, I have these 4 addresses in my segment routing header, it will generate an additional 72 bytes of overhead. Now think from the SP perspective, where that, let's say, their customers are sending some small packets. If you add this much overhead on each of those packets, how much additional bandwidth that it will consume from, let's say, this overhead perspective. Whereas all they need to go is to go to this block and then find these. Oh, by the way, I said 4 addresses of 72 byte. I think here I'm using 5. But anyway, I think you got the logic, right? So what I can do is, let me clear this ink. So if you see that, what I will say is you go to this block and then you go to 1, then 2, then 3, then 4, 5, right? And that's how you can execute your instructions, right? So you see from here to here, the purpose is same. This also traverse via the same path till 5, right? But I was able to compress all of this information into this address. I mean, this information, right? That way, I can save that overhead. This is called Micro-SID. You need to do a proper planning for this. Again, this is not a design discussion, but you allocate regions like this, and then you assign these IDs to your node, right? So that's how you can do this. Now, if you recall on the previous slide, we removed some instructions. Let's put those back. So from R4, let's say this is R4. I reached to 2, then 3, then 4. And then this is a local SID where I say that from 4, you need to use interface 1. Reach to 5, and then you need to use E000, which is like is function that I am allocating to VRF1. So I can see that, okay, when my packet is on node 5, this is the function that is telling me to forward it to VRF1, right? We will open up this more, but the purpose of this slide was to make you understand Micro-SID. I hope you understand that. So this is how basically your Micro-SID looks like, as we had seen. This is your first 32 bits. That's a block. And then each USID is encoded into these 16 bits, right? So with that, what I can do is I can encode up to these 16-bit USID in one carrier, okay? And there can be a global USID versus a local USID, but we will look at that in our upcoming slide. But here you see how your USIDs are encoded here. So it will follow the same path, 1 to 2, 3, 4, 5. Once it reaches on 5, this instruction or this function will get executed, right? But as I said, there can be up to 6 SIDs in this. What if there are more? Let's say I have these weird instructions where I say the go from 1 to 2, 3, 4, 5, 6, 7, 8, 9, then A and B. All these nodes you need to pass. But I told you in the last slide that we can only encode 6 USIDs in one carrier instruction. How you will do this? Well, we can use multiple carriers for that. So what I will do is I will split this, and up to 6 I will have it in this carrier, and then from here to here I will have it in this carrier. And what I will do is I will use this SRh and I will put it here. The same way we had seen in our previous slide, where individual SIDs were there in SRh, we can put these carrier things as well. And once this is over, like 1 to 2, 3, 4, 5, and 6, once I'm on 6, I will see that are there any segment left. So if there are segment left, what I will do is I will move this destination address here. These SIDs are actually executed in shift and forward manner, but I will cover this. But here, if there are more SIDs, this is how they can be taken care. Now let's understand how does this SRv6 packets get forwarded and what is this shift and forward. So now onwards, we will only focus on this micro-SID because that is the way SRv6 will be deployed. And we will see what is this shift and forward. So here you see, I have this IPv6 network, and this part of the network is coming from the block FC00AA. So all of my addresses for the node will be allocated in this block. So I have allocated 400 to node 4, 600 to node 6, 800 to node 8. Likewise, it will be 700 here, 600 is already there, 500 like that, right? But now, so this I can assign with that locator command that you see here, right? So this is how I will allocate the SID on node 4. Similarly, other nodes also, right? So now let's see how does the packet forwarding work. So here I have a simple instruction that packet enter from R1 need to exit from R8, and then it need to pass through, because this is your block, if you recall, 32-bit, and these are all 16-bit. UN, we call it as UN, and stands for node. So it need to pass through 400, then 600, and then 800. And after that, these are all zeros because we need to complete that IPv6 address, right? So those bits should be occupied. Zero means it's end of that carrier. So what will happen is on R1, we will look at our first block, which first these 16 bits, and we see that we need to forward the packet to this /48 address. In SRv6, you will see multiple node type. So this is like your source node where the packet is originated. These are all your transit nodes, which are simply executing those instructions. And then this is your endpoint node, right? Where the SRv6 header is taken off, and it, like if it is VPNv4, it decapsulate and forward the IPv4 packet on the respective VRF. So here, what we will do is on the source node, we will start with this. Then packet comes to R2. R2 will simply do this IPv6 routing lookup. That means it will look for this address and it will see that it is learning it from R3, so it will send here. Now, unlike MPLS, where if you are enabling MPLS, each of these nodes need to support MPLS forwarding. But for SRv6, another advantage is only this node, or where the packets, like if I am including some intermediate hop, like R4 in this case, need to understand SRv6. Rest of these nodes like R3, R2, they can simply route IPv6 packet. If they don't understand SR, it's completely fine. For them, it is just plain IPv6 routing. So R2 will look for that, will forward it. Then R3 will do the same, simple IPv6 forwarding, will come to R4. Now R4 will see that 400 is locally connected to me. This block is originated by R4. Now listen to me here very carefully. So once R4 sees that this is locally connected, what it will do is, as you see here, this is 400. It will do the shift and forward. What I mean by shift is it will eliminate this and it will move on to 600 like this. So 400, the place will be taken by 600, and then we will add 4 zeros, 16 bits, towards the end to make it like a end of carrier. So this is your shift and forward. Your 400 will be removed and it will be 600, and now this node will start look for 600. So packet can go either this way, depending on the routing. This is the shortest path, so packet will come directly to R6. Then R6 will perform the same. Now R6 will see that this is locally connected. It will perform shift and forward. So shift from 600 to 800 and then forward the packet. So you see here, it shifted to 800 here, and we again add these end of carriers towards the end, and the packet is sent towards further by doing the routing lookup where is R8 connected. So it will be forwarded towards R8. When it reaches to R8, it sees that this is locally connected, and then it will see, are there any further instructions? There are nothing, right? So the packet is destined to it. If it is VRF, again, we will see that example in the upcoming slide, but then there will be some local SIDs here. But before I go there, I hope you understand this forwarding. We will come to the VPN example. How does that exactly work? But let's first understand these blocks now that you see here, right? All these blocks. So even these blocks are divided into two parts. So these block, as you see, I'm just talking about that block 0100. This is 16 bits, right? So even these 16 bits are divided in two parts. The first range of this normally, that's what I had seen in the implementation for different vendors. The first part is global SID, which is like represent a specific node. For example, this 0100, right? And this once we have this is globally significant usage, and routers will follow that IPv6 routing to find out the path. Right now, if you go back in the previous, like this session, where I said that there is this locator and then there is this function also. Like once you reach on that node, final endpoint node, what you need to do there, right? That is the function. So that's where there are these local sets, local block, which are like the first uh, part or first range of these 16 bits are like global, and then the last some range, let's say, starts with, for example, E001, right? Because these are all hexadecimal numbers, right? IPv6 address we write in hexadecimal. So let's say E001 is your locally significant block on that. So it will tell that what exactly it needs to do when it reaches that node. And if you are familiar with SR-MPLS, think of it like node SID and adjacency SID, right? Same way. So now let's understand this. Now we understand this global block, local block, right? So again, the same topology. I don't need to explain it again. From source address is this 8, destination is 5. It will take this path. Simple. If I add the VPN into this, let's say, so what I will do is I will add this E025, and this E025 is assigned to VRF, let's say 1. So once I reach here on R5, I will again further look next and I will see that E025, that means I will send it to this VRF. Again, into this, if I want to add some traffic engineering, let's say I want to pass this traffic via R6, we can even do that. So it will go through 1, then 6, then 5, and once it reaches on node 5, this is your local SID, local block, right? So then it will execute and forward it here on VRF, whatever that SID is allocated for. I hope this is more clear now. So on SRv6, we can create layer 3 VPNs, layer 2 VPNs, as I was saying earlier, right? It support all those functionalities. So let's see how L3 VPN services are given over SRv6. So SRv6, let's say this is a simple provider network, right? Where earlier we were running VPN v4, but now we have enabled IPv6 here, IPv6 here. And on the same BGP VPN v4 address family, which is over IPv6 now, by the way, I will say that from site A 100 to 200, this 200 is reachable via this P33, and then once you reach to 33, do the lookup in VRF2. Again, a hypothetical example. These should be some hexadecimal bits that you should see if you are looking at original router config. So what will happen is my source address is this, destination address is 222, packet is coming from site A. It will get encapsulated with the IPv6 address where the source will be this, destination will be this P, and then this P in between will simply do IPv6 routing. So once it reaches here, I hope by now you understand, it will be forwarded to VRF2. So your packet get encapsulated. Once it reaches 3, it will see that it need to forward to VRF2. It will decapsulate and send the packet. So that's how it works with SRv6 at a very high level layer 3 VPN example. It's as you see, it's a single SID. My VPN label, my transport label, I am just using one IPv6 address for that. I have split it into locator and function. So only one single SID is used. BGP already have support for IPv6, so there is nothing that is needed on the BGP side, and I don't need any other protocol. It is as simple as that. We just need IPv6 forwarding, right? So I hope this is clear. And then on the segment routing, right, V6 for SRH, I had shown you like usage, multiple of those usage in a single packet. But ideally, most of the use cases, as we had seen that L3 VPN, right, don't even need SRH. It can just work with that one single SID, L3 VPN, L2 VPN, EVPN, right, egress peering, or even if due to some traffic engineering or some other requirement, if you need SRH, it can be one or two nodes, one or two SIDs. So I think we are close to 1 hour in this session. We can stop this here. I will further record some more sessions, but I hope this was useful for you. And I would like to say thanks a lot for viewing this.